Alright guys, let's move on now. The related samples t-test, as I told you, grabs the same group of people and tries to test them twice. So now, I'm interested to see if the online component is going to affect the grades of my statistics students. So half of the semester was the students taking the class face-to-face, half of the semester was the students taking the class online. That's the distinction, that's the difference. The same group of people are being tested before and after. If that's your interest, then you should go with the related samples t-test. Heads up, the related samples t-test typically has a bigger probability of finding a difference. It tends to be a stronger difference because you reduce a lot of variability by using the same group of people twice. The problem, and I will highlight this in other sections of the course as well, the problem is that it's hard enough to get people to participate in your studies once, so to believe that you can get them twice can be kind of hard, but that may be something of your interest. Well, same thing that we did on the independent samples t-test. What is your null? What is your alternative hypothesis? Your null hypothesis is saying that there's nothing changing, and your alternative is saying that there is something changing. If I'm interested in knowing if my students are going to change differently depending on the class going online or not, my null will be something like students will not have different grades after the class goes online. That's my null. And my alternative is students will do differently after the class goes online. My null is saying that there's nothing going on. My alternative says there's something going on. Right? Now, once we have a criteria set, I forgot to write here, degrees of freedom. In the criteria, the alpha level, like we said, is the percentage of error. Typically it's kept at 0.05, but it's really up to you. If you want to go lower than that, then you must have a really good reason to say that you're going to find a difference. Typically, most researchers keep it at the standard 0.05, 5% of chances of error. Degrees of freedom, n-1 implies that the sample that you're collecting, if I have 25 students in the semester, I'm only going to use the same students that come back the second time for the test. If, say, before going online I had 25 students and after going online I only have 20, those 5 extra scores, I gotta discard them. They're not useful. Gotta make sure that the same group of people are being tested twice and I'm not changing the people. So if I have 20 in one end, now I'm gonna have 20 in the other one. It's gonna be 20 minus 1, you know? One-tailed or two-tailed, are you going to say that there's going to be a difference? It's going to make it a two-tailed? Are you going to say that the difference is going to go up or is it going to go down? Does make it a one-tailed? And it can be positive or it can be negative like we said before. One-tailed, saying that there's a direction, is directional, and it can be saying improve or worsen, increase or decrease, reduce or grow, whatever. And then based on that is where you have your critical value. It's going to be 0.05, your alpha level. Is it going to be a one-tailed or two-tailed? You can see it at the top. And then on the side is where you're going to see if it's going to be, if it's going to be degrees of freedom of 8, 9, 10, 12, 15, 60. Really depends on you. The key thing here, the key thing to compute a related samples t-test is to find the uppercase D, the big D. Uppercase D is the differential of scores. You can see this on the slides. If I'm interested in knowing the grades of students before and after going online, I have 20 students here. And I have a student 1 had a 74, a student 2 had a 84, a student 3 had an 85, and so on and so on. I'm going to compare this to the grades of my students in the second group, the students after going online. Now, student 1 got a 84, student 2 got a 85, student 3 got a 76. And I'm going to subtract one group from the other one. I'm going to take the differential of the scores, compare the group the first time versus the second time, and that's going to be the D. Once I add up all those different scores, that's my D. So once I have all those scores, if I square them up, sigma, remember, is for addition. So once I have all the differential scores, if I square each different number and I add them up, that's going to give me the number. If on the other hand, my second group of scores, I just add up the differential, and the differential is being squared, so perhaps of all 20 students, overall the D was 80. I square the 80 divided by the number of students that I have, which is the n. I had 20 students, I have the n there. I'm gonna divide that by n minus 1. That's gonna give me this number. This number is the variance of the D. This number is going to be the variance of the D. Now, heads up. Once you get the variance, subtract the variance, take the square root of the variance. That's going to give you what is like the standard deviation of the differential. This number is going to be important, and you'll see it in the next video. That number is important because it will help you out on the effect size measure. Now, when the numbers are here, once you find the variance of the differential, you're going to see it there. You're going to divide it by n, which is the number of people that you had in your groups. Take the square root of that, and that's giving you the estimated standard error of the differential. Lastly, you're going to take the average of the differential. If in the differential I had 150 of a differential, and I had 10 students, 150 minus 10 is going to give me an average of 15 points in the differential. That is the number that we're going to go here. That is going to be divided by the estimated standard error, which is going to give me my obtained value. The number that you get here is going to be compared to the critical value, same as we've done before. So, based on this number, based on this outcome, do you reject or fail to reject? If the number here is positive, then you want a number that is more positive in your obtained value. If your number here is negative, then you want a number that is more negative. We've done it before, you know how it goes. That is how you compute a related samples t-test. This thing here is what is hard, I know. This may be confusing, and as I'm saying it without putting it up on the board, I know that it may sound difficult. Look at the slides. It's going to show you step by step. Look where the number comes from, and you're going to see where the number is. And then let's work on the class activity so you have some practice on it. This actually is far easier, at least for me, than the independent samples t-test. And this one is more reliable than the independent samples t-test. The hard thing is making sure that the person that is participating in the study comes back 2 times. But if you can get that done, I recommend this far better than the independent samples t-test. Good work, guys.